Okay, so let's unpack this. Welcome back to the deep dive. Today, we're doing something a little different, something we rarely get to do. We're holding up the actual architectural blueprints for a massive, cutting-edge machine learning system. And this isn't just some conceptual whiteboard drawing. This is the real end-to-end specification for how a discovery intelligence engine operates in the wild.
It really is. That blueprint, the Discovery Intelligence Industry-Ready System Architecture Specification V1.0 it's incredibly complex, but it paints such a complete picture.
Right.
It shows how modern specialized AI moves way beyond just the simple proof of concept. It's the answer to that big question. How do you take these massive volumes of messy real-world data?
Things like patents, chemical structures.
Exactly, and transform all that raw chaos into reliable, continuously updating predictions.
And that's really our mission for today. We are going to dissect the 5 major layers of this architecture. We'll go from the initial raw data intake all the way through to the serving layer, and I think crucially, that self-correcting feedback loop at the very end. We need to understand what specific combination of specialized tools and generalized cloud infrastructure allows this blueprint to so confidently call itself industry ready.
And what's so fascinating to me here is the blending of worlds. This system isn't, just a standard database setup that's been bolted onto as a simple Python model.
No, not all.
It's a truly integrated pipeline. It demands big data scalability. We're talking petabytes here, and pairs that with these advanced, very specific AI models, in this case, graph neural networks. And it's all wrapped up in these rigorous MLOps practices for quality control.
And if you connect this to the bigger picture, this kind of architecture, it just reflects the non-negotiable requirements of modern high-stakes data science today. We're talking about absolute traceability, massive scalability. You often see it relying on global cloud standards like Kubernetes and Fargate for containerization. And then there's the requirement for continuous iteration, making sure the models never fall behind the science. It has to be a living, breathing system. So let's start at the foundation, the place where everything begins, the input data. In the diagram, this is represented by the blue and yellow zones. This is the data acquisition and the lakehouse layer.
Okay, so in that blue zone, we see these highly specific sources, and that immediately confirms the domain we're in. It's pulling data from external DDs, and they specifically name Chembl.
Which is the gold standard for bioactive molecules?
It is. Yeah. That immediately signals we're in the realm of, say, chemical or drug discovery.
And then that second source, literature patents, that's a whole different ballgame. That requires dedicated scraping processes. It's not neat transactional data. It's just dense, unstructured text that needs to be mined.
Yeah, and how they pull it is interesting, too. The whole acquisition process is handled by Python, ETL extract, transform, load scripts. And they're scheduled using these really robust tools like Apache Airflow or Prefect. They ensure not just regularity, but real efficiency by using Poolel methods or even CDC.
Okay, let's just pause there. For someone listening who hasn't encountered it, what does using CDC, change data capture, what does that signal? Why is that detail so important in this foundational blue zone?
CDC is absolutely critical for scale. It means the system isn't wasting resources reprocessing entire databases every single night. It only captures and pulls the changes, the new molecular entries, the updated patent filings.
So it's efficiency in practice.
Exactly. You only process what's necessary. In that raw input, your standard JSON or CSV files, that lands in the S3 landing zone. But like you said, that data is still raw. It's what we'd call bronze data.
Exactly. It lands as raw material, completely unusable for training an AI. And that's where the yellow zone, the data lakehouse, steps in to perform the true alchemy, right? Moving from bronze to silver data.
The lakehouse is the refinement layer. The first step, data cleaning and standardization, uses the tool of choice for big data, Apache Spark. But here's the massive architectural insight. They pair Spark with RDKit UDS user-defined functions.
Whoa, okay, wait. So they didn't just dump this into some generic cleaning service. Embedding RDKit UDS directly into Spark. That sounds like a huge investment in domain specificity right at the infrastructure level.
It absolutely is. I think that's the core insight in the yellow zone. They are prioritizing domain rigor over generic speed. RDKit is the fundamental library for cheminformatics. Using RDKit UDFs within Spark means they are performing incredibly complex molecular processing.
Like what? Validating smile strings, calculating fingerprints, that kind of thing.
That's it. Or normalizing chemical structures. And they're doing it at a massive distributed scale. They've guaranteed that even when you scale this across hundreds of compute nodes, the chemical reality of the data isn't compromised.
So the output of this highly rigorous cleaning process is the silver data, stored efficiently in Parquet and snappy formats. But silver still isn't what the model actually eats. And this brings us to what I think is the most architecturally unique step, the alchemy of turning silver into gold feature data.
Right, and that's the feature engineering and graph construction step. This uses Python and, crucially, PyTorch geometric. This layer takes the cleaned molecular data and converts it into these complex relational structures, graph data, which are then stored as gold data, as .pt files, in the S3 feature store.
Okay, so why that commitment to graph construction? Why is that conversion the necessary step for the GNNs that we know are coming up in the next zone?
It's because graph neural networks are designed to model relationships, not just entities. Let me try a simple analogy. A traditional ML model, it treats a molecule like a flat list of features, like just listing the ingredients in a cake.
Okay.
A GNN, using graph construction, treats it like the blueprint for the cake. It's not just what atoms are there, but how they bond together, what shape the structure takes, and what neighboring atoms influence stability. That relational understanding is the absolute key to unlocking true discovery intelligence. It allows the AI to learn from the structure of the data, not just the isolated components.
We have spent a lot of time preparing this perfect, structured gold data. Now we transition into the engine room, the pink zone, the MLOps platform. This is where the actual intelligence, the models created, and maybe more importantly, rigorously managed.
Precisely. The core of it all is the GNN model training pipeline. The training run itself is triggered by an event, the arrival of new gold data in that S3 feature store. This shows the system is reactive, it's always eager to learn from new knowledge.
And the infrastructure is optimized for burst computing. I see they're running on GPG Spot instances. For our listener who might not be deep into cloud architecture, why Spot instances here? That just screams cost optimization to me.
It is entirely a cost optimization play. Training large GNNs, especially on these complex molecular graphs, it requires huge bursts of GPU power, potentially for hours, even days.
Right.
Spot instances let them leverage spare cloud capacity at a fraction of the cost. They just accept the slight risk that the instance might be interrupted. But the MLOps platform, using Airflow for orchestration, is designed to be highly resilient. It's checkpointed to handle those interruptions gracefully.
And the tooling stack here seems critical for actually operationalizing the system. They're using PyTorch for the heavy lifting of the model training itself, but the management side relies heavily on the MLOps platform, primarily MLflow and Airflow.
Yes, and MLflow is just crucial for reproducibility and traceability. Captures everything, the logging metrics, the exact hyperparameter settings, the resulting model artifacts from every single training run, and it directs all of that to the MLflow tracking server.
Yeah.
This is essential for auditability. If a discovery goes sideways 2 years from now, you can trace exactly which model version, trained on which gold data set, made that prediction.
Okay, so once that intense training run is complete and the model becomes an MLflow candidate, it still has to earn its spot in production. This is where the system's quality control kicks in. How does the architecture ensure the model is truly ready before deployment?
First, it moves to the model registry for version control. Then, it enters the evaluation service. This service runs an automated eval against a non-negotiable source of truth, the golden test set. This isn't just any data. This is the curated, definitive benchmark that defines what success even means.
The golden test set is crucial, but isn't it also a potential weak link? I mean, if you bake the test set into the model's history, how do you guarantee that set itself isn't subtly leading to a performance plateau or some kind of bias over time?
That's a very sophisticated governance question, and the architecture addresses it indirectly through tracking. Promotion to deployment control is only granted if the model meets the required performance level, which is tracked in the state DB using something called the curriculum state.
Curriculum state.
Yeah, the curriculum state manages the model's progression and its evolution. It ensures it's not just passing a single test, but mastering a sequence of increasingly complex challenges, much like a student moving through a syllabus. It tracks how the model handles different data distributions and tasks over time.
This really raises an important question for you, the listener. This level of structure, it guarantees not just a trained model, but a validated and tested one that can demonstrate mastery over a challenging curriculum. In discovery science, where the stakes are multi-million-dollar investments, that structured validation drastically reduces risk. We've built and rigorously validated our machine learning engine. Now we need to make its predictions accessible. We move to the green zone, the serving layer. This is the user-facing deployment.
And here, reliability and speed are paramount. The deployment control system takes the approved, validated model and packages it into a containerized service. This is all deployed using industrial-strength container standards, Docker, Kubernetes for orchestration, Fargate for serverless scaling, and an application load balancer, or ALB, to distribute traffic.
So if one instance fails, another just takes over instantly. And the actual predictions are handled by a fast API inference service. I appreciate the choice of fast API here. It's designed for high-speed, modern web APIs, accessible via standard REST post calls. And the input it accepts is standard chemical notation, specifically SMILE strings.
Right, SMILES is just the text format that describes a molecular structure. It's basically the industry-standard way of writing down a molecule. So a researcher can hit this API with just a text string and the output. Well, the output is where the real insight surfaces. The service delivers two crucial pieces of information. The prediction, naturally, but also the uncertainty.
And here's where it gets a little philosophical. The delivery of that uncertainty alongside the prediction is so key for decision-making in discovery intelligence. It's not just an answer, it's an answer and a warning label. It fundamentally shifts the system's responsibility.
Absolutely. The system is essentially saying, I predict outcome X, but based on the statistical distribution of the data I used to learn, you should only trust this result. Let's say 80%. That uncertainty score tells the researcher if the system is extrapolating wildly into the unknown or if it's interpolating confidently within what it knows. It changes the entire risk calculation for the human decision-maker down the line.
So the journey seems complete when the prediction is delivered, but the architecture doesn't stop once the prediction is made. It immediately loops back, bringing us to the final and I think the most forward-looking layer. The purple zone, the feedback loop.
This is truly what makes the system industry ready, its capacity for self-correction. It ensures that the model we just deployed, which was perfect yesterday, doesn't immediately become stale tomorrow.
So what does this all mean for the operation? Well, the self-correction starts with logging. Every single prediction made by that fast API service is logged asynchronously. It uses high-throughput streaming tools like Kafka or Kinesis via an inference logger. This creates a massive real-time stream of model behavior and production data.
And what's watching that stream is the automated watchdog, the data drift detection component. This critical piece uses Spark streaming and statistical tests to constantly monitor the prediction stream for changes. It's looking for data drift threshold.
So that detection system isn't just checking if the model is still performing well on old static data. It's monitoring if the real-world input data, the live SMILE strings coming in, or if the resulting predictions are changing in a way that suggests the model is no longer accurate. It's checking if the world has moved on from the model's original training data.
And this is so vital in fields like chemistry, where the discovery space is constantly expanding. The alert from the data drift detection component acts as a trigger DAG, a directed acyclic graph, which feeds right back into the pink zone, right back to the GNN model training pipeline.
And that's the moment of truth. The machine has noticed its own decay and automatically initiated its own replacement, forcing a complete retrain using fresh data from the gold feature store.
This demonstrates a truly closed-loop system. It ensures continuous evolution. The system itself is responsible for detecting its own degradation and initiating its own maintenance cycle. This moves the bottleneck away from the human data scientist who would have had to constantly monitor model performance manually.
That was a tremendous deep dive through a very, very dense architecture specification. To sort of synthesize what we've learned, the system starts with raw patent text and shim belt data, and it focuses on domain rigor by refining it with specialized cleaning via RDKit UDX right inside of Spark.
It then converts that refined data into these complex structural features using PyTorch geometric, creating the relational graph data. Then it subjects the resulting GNN models to really rigorous management using that MLOps triad of MLflow, Airflow, and the crucial golden test set tracked by the curriculum state.
And the results are delivered robustly and scalably via fast API on containerized infrastructure like Fargate. And importantly, it includes that vital uncertainty score to inform human decisions.
And it all culminates in that vital automated feedback loop, detecting decay via data drift and forcing a hands-off continuous retrain. The value of this architecture is precisely its seamless integration. You have specific high-end tools optimized for the domain RDKit, the GNN's packaged within generalized industrial cloud infrastructure S3K8's Spark. This guarantees both precision in discovery and guaranteed operational scalability.
So here is our final thought for you to chew on, and this pulls directly from the power of that purple zone. If a machine learning model is constantly monitoring its own decay and automatically initiating its own replacement by triggering a retrain, does that fundamentally change the role of the human data scientist? Does their job shift almost entirely from executing the training, the hands-on labor, to governing the automated pipeline, to ensuring the rules, the thresholds, and the curriculum state are philosophically sound? We'll leave you to consider that shift until the next deep dive.